So, let us continue our study of functions of two variables. In fact, the study of calculus of functions of two variables goes parallel to the study of calculus tools for functions of one variable. If you recall, for a function of one variable, we defined what is a function of one variable, we looked at the domain, what is the range, then we looked at the graph of a function of one variable, and then we started looking at the concept of limit, continuity, and differentiability and its applications in economics. One can develop various rigorous tools for analyzing what is the meaning of limit of a function of two variables, what is the notion of continuity of functions of two variables, and so on. The only thing is, once you have defined the notion of limit, everything else follows. But this being not a course in calculus of several variables, will not go into all those details, but will try to utilize maximum possibly the notion of calculus of one variable. How does it give results in analyzing functions of two or more variables in the applications in economics, commerce, and management. So, at some points I will just give you a reference of what I am assuming and what we are going ahead. So, the basic idea is that for a function of two or more variables, one would like to utilize what is the what are the results that we have already developed for function of one variable. That means, given a function of two or more variables, we should try to bring it down to function of one variable, and that is not difficult, as we can do it as follows. So, what we are saying is, some of the properties of the function of two variables can be analyzed by assigning some fixed numerical value to all but one variables. So, given a function of say two variables, you fix one of the variables, assign some particular value and analyze, then it becomes a function of one variable only. So, all the tools available for one variable calculus will be applicable. This does not give you everything, but most of the things required for applications, this is good enough. So, let us start looking at f is a function of two variables f x y. So, let us fix the variable x as x is equal to x naught. So, the value of the variable x is fixed with x is equal to x naught. So, we are going to calculate what is f of x naught comma y for all y. So, x naught is fixed. So, only y is changing. So, this becomes a function of one variable y going to f naught of x y. So, this becomes a function of a single variable. Similarly, you can fix up y equal to y naught and then look at the values of f x comma y naught as x varies in the domain. So, of course, you have to look at x comma y naught in the domain. Here also you have to look at all those points x naught comma y in the domain of the function. So, fix up a point x naught, you get a function of the variable y, and you fix up a value of y naught, you get a function which depends only on x of a single variable. So, these are the two functions. They do not give complete information about the function, but they give a reasonable amount of information about the function. So, these functions normally are called the coordinate curves for the function, because in some sense you are fixing one of the coordinate x 0 and let the other coordinate y vary. Similarly, one coordinate y is fixed at y 0 and x is allowed to vary. So, these are called the coordinate curves. We will not be having much opportunity to use them, but anyway. So, let us look at a function of two variables f of x y equal to x y divided by x square plus y square. Of course, to make it so that this is defined everywhere, this formula does not give you the value at the point 0 0. At every other point when x y is not 0 0, this formula makes sense. So, the function is given by this formula when x y is not 0 0 and is given equal to 0 if x y is equal to 0 0. So, let us try to find out if you fix up say the x coordinate or the y coordinate at 0, let us say. So, let us fix So, here is a statement which is a continuous in each variable at x 0 y 0, but it is not continuous at the point a function of two variables. So, let us just have a look at it what we are trying to say. So, let us look at the function. So, f of x y is equal to x y divided by x square plus y square. So, this is y square if x y not equal to 0 0, and it is 0 if x is equal to 0 is equal to y. Right. Now, let us fix x is equal to x naught. Then what is the function? F of x naught y is a function y going to this. So, what is that equal to? If x naught is not equal to 0, then the function will be x naught y divided by x square plus y square, right. So, that is a function of the variable y, and if x is equal to x naught is equal to 0, then what is the function? Y going to f of 0 y. So, what is f? That means x is equal to 0. So, it is 0 into y is 0, whatever be the denominator, it is 0 for every y. So, this is for every y. So, for the value x is equal to x naught fixed, if it is not 0, this is the value, and this is the value if it is equal to x naught is equal to 0. Now, so we are looking at this. So, this as a function of y. So, look at this function, this as a function of y. We can ask the question, this as a function of y, is it continuous at the point y equal to 0? So, that means what? If we let y go to 0, what will happen? By the limit rules, whatever be x naught, y goes to 0. So, numerator goes to 0. So, this goes to 0 and the value at 0 is 0. So, this as a function of y is continuous at y equal to 0. Okay. And similarly, we can analyze what is the function when other point is fixed, right. So, what we are saying is when you fix the point, so this is continuous at 0 0 in each variable. That means, if you fix one of the variables as x naught, then it becomes a function of y, and that is continuous at the point 0. Similarly, as a function of the other variable with y naught fixed, it is a function of x, that also is continuous as a function of one variable. But one proves, we have not defined what is the continuity of a function of two variables, but one proves that this function is not continuous as a function of two variables. So, what I am trying to give you is that when you restrict a variable in a function of two variables, it gives you some idea about the properties of the function, but it does not give you complete idea about that function. For example, this example tells you that once each variable is fixed, it is a continuous function, but when you jointly, it is not a continuous function. So, something is missed when you restrict your attention to a particular variable, but still fixing a variable and analyzing it gives a lot of information. So, however, these are the coordinate maps, x going to f of x y naught when y naught is fixed, and the other is y going to f of x naught y when x is fixed at x naught. These are the coordinate maps. They give us some useful information. We will see what are that information. For example, look at this the following way. If a function, if one of the coordinates maps is discontinuous at a point x naught, then the function itself cannot be discontinuous, cannot be continuous at that point x naught y naught, because there is a break in some sense in the graph. So, these are the kind of informations, these are useful, that if a function is not continuous, one can prove these things rigorously. We are not going to do that, but I am just trying to give you an illustration that fixing one variable at a time does give you some information, if not about continuity, it gives you information about discontinuity. Namely, if a function of two variables, when one variable is fixed at a point say y naught and it is discontinuous, then it cannot be continuous at a point x naught, y naught, and so on. So, to understand how does f x y behave near a point x naught, y naught, one can analyze differentiable properties of these functions and so on. So, let us what we are going to do next is going to look at we fix one variable at a time and look at the coordinate functions and look at their differentiability properties. Let us see what information can we get out of that. So, here is a function of two variables x naught, y naught belonging to D is an interior point in the see whenever we want to look at continuity differentiability, we normally look at the interior points in the domain, not the end points, not the boundary points kind of a thing. So, that you are able to move around in a neighborhood of that point. Okay. Geometric is a function. So, this when you fix variable y naught, what are you getting? Y naught is fixed, that means at the point x goes to f of x naught, y naught, that is a function of one variable. So, that is a curve, that is a curve in R3, right. So, this is no longer a curve in the plane, it is a curve in R3. And what is that curve? This curve is nothing but the intersection of the surface z is equal to x f x y with the plane y equal to y naught. See, so visualize there is a surface, the graph is a surface, when you are fixing a point y naught, right, and you are looking at x, we are varying x. So, you are actually moving along a line, x is varying. So, you are moving along a line, x is varying, y naught is fixed. So, you are moving along a line in the domain and you are looking at the values of the function at that height, okay, by the plane when it cuts that surface. So, this is a curve in the, so z is equal to, so x goes to f x y naught, this x y naught is a point which lies on the curve, on a curve which is in the, is a point on the, is a image. So, it is a image point for the function. So, it is a point on the surface. So, as x varies, this gives you a curve on the surface, okay. And geometrically this curve is nothing but the intersection of that surface, that is a graph, with the plane y equal to y naught. So, similarly, when you fix the other one, other variable as x naught, you get a curve on the surface which is the intersection of the plane x is equal to x naught. So, we have to now visualize what we are doing. So, let us look at a picture of this. So, this is the picture. So, imagine this is the R3, right. Here is a domain. So, this is the surface. So, this is the surface, the green one is the graph of that function in the domain. So, at a point x naught, y naught, if you fix x naught, that means this point x naught is fixed. You are able to move along this, right. You are able to move along this point, x naught is fixed. So, what is if x naught is fixed, y is allowed to vary. So, y is allowed to vary means you are moving along this line, you are moving along this line, x naught is fixed. So, when you move along this line, for every point you will get an image, for every point you will get an image, for every point you will get an image. So, you will get a curve on the surface, and what is that curve? That is as if you take this plane passing through this point and going up. So, look at the plane x is equal to x naught raised up and intersecting with the surface. So, that is a curve, right. So, that is the that is how the you will visualize the range of a function of two variables when one variable is fixed. Similarly, when you in this when you fix y naught, then what you are allowed to move is along this line in the domain. When you move along this line, the point, each point will give you a point on the graph of the surface, on the graph of the function, that is the surface. So, we will get a curve here, right. So, this is and what we want to know is, so you get two curves, right. So, this is the domain and that is the curve. So, it is a function of one variable. You can ask whether this is differentiable at the point x naught, y naught. Similarly, whether this is differentiable at the point x naught, y naught. That means what? So, when you are fixing x naught, you are looking at as a function of y, you get this curve, and at this point whether it is differentiable, meaning at this point as a function of y. So, y equal to y naught, whether there is a tangent here or not. Similarly, for the other case, when you are fixing y naught, you are fixed y naught, you are moving along x. So, you get a curve. So, whether you are getting a tangent at the point x naught, y naught. Let me try to show it a visualization of this, the partial derivatives. So, look at, so this is the surface. So, when you fix x naught, okay, you are moving to move along this curve, and that curve is the one which is x naught y. So, at this point you want to know the tangent. Similarly, for this you are moving, okay, moving from a point y naught, you will get a curve, right, as x varies, and you want to know whether at that point there is a tangent possible or not. So, let me show you once again. This is the surface, that is the graph of the function at a point x naught y naught, right. If we fix x naught, if this point x naught is fixed, you are allowed to move along this line only. So, once you move along this line, you will get a curve which is z is equal to f of x naught y, y is allowed to vary. This is the point f of x naught y naught, and saying whether this is differentiable at this point or not means whether at this point you are able to draw a tangent or not. So, that is what we meant by that. So, whether a tangent is possible at that point or not. So, that is the notion of differentiability for a function of two variables when one variable is fixed and the other variable is allowed to vary, right. So, similarly, you will have the one point y naught as fixed and x is varying. So, you will be allowed to vary along this line. So, once you vary along this line, you get a curve, and at this point on this curve, which is f of x naught y naught, you want to know whether the tangent exists or not. So, this is so let us make it mathematically precise. What we are saying is, for a point x naught y naught in the domain, an interior point of course, look at f of x naught plus h y naught. So, that means what? You are keeping y naught fixed at both, you are looking at the value at the point f of x naught plus h comma y naught, and the difference f of x naught comma y naught. So, you are looking at the increment in the function in the direction of x axis only, y naught is fixed. How much is the increment? H. So, this is the rate of change of the function in the direction of x axis at the point x naught y naught. So, limit h going to 0. So, this we will call as the partial derivative of the function f at the point x naught y naught in the direction of the variable x, because x is varying, y naught is fixed. So, once again we are trying to understand what is the rate of change of the function of two variables in the direction of along x axis. So, when you say along x axis, you will change the values only along the x axis, but keeping the y, you will go parallel to the x axis, keeping y naught, y equal to y naught fixed. So, at a nearby point, the value is f of x naught plus h comma y naught. So, this is the increment in the function when you move from x naught y naught to a nearby point x naught plus h comma y naught and divided by h. So, that gives you the ratio of the change, and h going to 0. If it exists, that is called the partial derivative of the function f at the point x naught y naught, and we denote this partial derivative as f of x, x naught y naught. So, this is one notation used, that means for the function x, when the lower x, that means we are looking at the derivative, partial derivative, derivative with respect to the variable x at the point x naught y naught, and that means this limit should exist. So, that is a value equal to this, or this is also written as something similar to dy by dx. So, instead of writing dy by dx or df by dx, we write this Greek letter called partial. So, del f, so this is also called del. So, del f by del x. Okay. So, this is called the partial derivative of f with respect to x. So, this symbol is called the partial. So, partial f divided by partial x, the partial derivative of f with respect to x at x naught y naught, that is this limit, if it exists, that is called this. So, this is the partial derivative of the function f in the along the variable x at a fix y equal to y naught. So, whenever it exists, this is denoted by this value. We can have something similar for the other variable. So, let us similarly we can define the partial derivative of f with respect to y at the point x naught y naught to be the limit, that is x naught is fixed. So, y is allowed to vary from y naught to y naught plus k. So, that is an increment in the value of the function as you go from x naught y naught to x naught y naught plus k, increment is k. So, take the ratio and take the limit like in one variable. So, we are treating this as a function of one variable. If this exists, this is called the partial derivative of f with respect to y at the point x naught y naught, or it is also as the other variable partial derivative del f by del y. So, this is either read as del f by del y or just say partial of f with respect to y at x naught y naught. So, these are numbers by the way. So, for a function of one variable, the derivative at a point is a number, is a scalar. Similarly, the partial derivative of a function of two variables with respect to either variable at a point is a number, right. So, let us consider our revenue function, that pharmacy example, where the revenue by selling two different kind of products was r x y equal to 1.25 x plus 1.50 y. Then for any fixed value of x to be equal to x 0, right. If x is equal to x 0, then the function is 1.25 x 0, x is equal to x 0, 1.5 y. So, with x is equal to x 0 fixed, this is the value of the function of two variable when y is allowed to vary. Now, x 0 is fixed. So, that means this quantity is a constant as far as the variable y is concerned. So, this is only a function of one variable. So, we can differentiate, apply the rules of differentiation of one variable and calculate its derivative. So, that tells us, because this as a function of y is differentiable. So, we get the derivative, partial derivative of this r x y with respect to y at x 0 y, whatever be x 0, the value comes out to be this gives you the derivative to be 0, and this part gives you the derivative 1.5 for all y. And similarly, the partial derivative with respect to y equal to y 0 fixed, if this is fixed at y equal to y 0, you will get the value 1.25 as the partial derivative at the point for every all values of x, the partial derivative at a point x 0 y 0 or any point is equal to same. So, it is, so this is how you calculate the partial derivative. The idea is you fix one of the variables, see what the function looks like, and see whether rules of differentiation of one variable are applicable, and accordingly calculate the derivative. Sometimes you may have to do it by the first principle as the limit, sometimes just looking at the function and you can apply the theorems of differentiation. So, this is we applied. So, let us look at consider an output function related to the quantities of inputs x and y as below, where q is a function of two variables x and y. So, that is 50 x minus x square plus 60 y minus 2 y square. So, this q that is output is a function of two inputs x and y and is related by this formula. So, this is defined for all x and y belonging to R, and it is a nice function, it only involves powers of x and y. So, this is what is called normally a polynomial in two variables. So, let us fix one variable and calculate so let us the partial derivative of q with respect to x. So, with respect to x means we are fixing the variable y, right. So, y is going to be fixed. So, when y is fixed, 60 y is fixed as a constant, minus 2 y square is fixed as a constant. So, as far as x is concerned, these are the only terms where x is appearing. This is a constant as far as x is concerned when x is fixed. So, we are looking at a partial derivative of q with respect to x. So, we will treat 60 y and 2 y square as a constant. So, what will be the derivative of this? with respect to x. So, dq by dx will be 50 minus 2x, and similarly dq by dx will be equal to treat this as constant and compute what is the value of the derivative with respect to y. So, this being a constant, differentiating with respect to y gives you 60 minus 4y. So, these are the partial derivatives of q, this output function with respect to the input x, and this is with respect to the input y. So, if you want, you can relate it with the marginals now. In one variable, we looked at the derivative to be as the marginal of that quantity, whatever the function we were looking at. So, here is the production function q as a function of two variables. So, we can call this partial derivative of q with respect to x, we can say is the marginal of productivity with respect to input x and with the input y as fixed. So, keeping the input y fixed, what is the marginal of the product function with respect to the variable x. So, that is partial derivative of q with respect to x. Similarly, if we keep x fixed, the input x fixed, we do not change the input x, keep it fixed at some particular value, and look at the partial derivative of q with respect to y, that gives you the marginal of the cost marginal of the product function with respect to the input y for the other variable x as fixed. So, these are the interpretation of the partial derivatives as the marginals. So, we will continue our study of partial derivatives and its applications in analyzing functions of several variables in scenario of economics. So, thank you.